Welcome to my presentation of my Capstone project for Advanced Data Science project from IBM. I'm Kasper and I'm gonna present my project. A really exciting project if you ask me. So what we've been doing is, what I'm gonna go through is basically two steps. We're gonna go through the stakeholders and then we're gonna go into the more nerdy stuff, why I did what I did, how I assessed the data, how it performed, and lastly, how the entire algorithm works. So the first thing we're going to do is, well, what did I do? What was the project about? The project was basically about subtracting areas of interest from pictures. It's what we call object localization, and it's focused around taking a picture, subtracting the area where we observe a skin disease, and then saving it. And then we can say, why not just go through the entire step and doing the classification as we're already having the picture and all that kind of stuff. But the reason why we're not doing that is because we're actually trying to do it as a part of a bigger project, about bigger mindset about what we're trying to do. Because melanoma is a time-sensitive disorder, as you can see through the A to C or A to E questions. A lot of it is actually, does it change? Is it their development? What's the trajectory of this mole I'm having? Is it going the wrong way? Is it even developing? So it's actually much more of a time series question than it is of a classification in the moment. Because trust me, when you see the pictures of skin disease, you'll know it doesn't look. You can tell that it doesn't look good. So what we're trying to do is do an earlier detection of melanoma using this algorithm instead of having to wait a couple of years before seeing the doctor. You can just keep taking pictures of it, and then the later algorithms should be able to detect, is it developing, is it changing something, should it be concerned. So that's what I'm trying to do with my project. What we got is a data set of clinical pictures, close to 23,000, which is a pretty big number when we're talking photo data. And it's all generated by experts, doctors, or either by doctors or consensus of doctors that have been sitting down and saying, okay, this is the segment, this is the disease. Is it benign, or can we just ignore it? Is it just a normal mole? So it's a pretty awesome data set if you want to do this kind of detection. Um, and that's basically all I use for this. I didn't generate anything on my own. I just used this data set because I thought it was high enough quality. If doctors think it's high enough quality, it should be high enough quality for a lonely nerd as me. The use case is basically when we're looking into a skin disease like this one, what is later developed to a skin disease. We would like to see this and then follow the development through time, and then actually earlier than a year before or year after, saying, oh, this is going the wrong direction. We should probably go see a doctor about it. So instead of waiting a year to see the development, or 2 years, how much time it'll take you to go to the doctor, it should be earlier detected. But that's not a part of this project. This is just detection. This is just finding the bounded boxes to be used in the later algorithms. When we talk about the solution, it should be just taking a picture of the skin disorder with your phone, feed it to the model, and then you get it will subtract the picture or the area of interest, and then save it to keep doing the other stuff, the other algorithms with time series analysis. Is it developing? How's it developing? What's happening with this mole I'm having? That's the solution. That's what we're trying. That's what I'm aiming for when doing this. When doing it, we could have done, or what I could have done, was going to end-to-end deep learning or using a YOLO model, which is basically it wouldn't have helped me a lot because it's a time series question when we're doing this kind of disease. So I could use that kind of model, look at it and say, okay, that's a mole, that's a mole, that's a mole, that's a mole. And then this is not a mole. You should probably have to check that out. but then the early detection wouldn't be considered, and we wouldn't go through the A to E detection methods or questions that doctors are asking. And also, we will lose a lot of data that way because we just focus on a smaller picture in order to feed it to your YOLO model. But the overall architecture of my model is based on the fast RCNN model. I just removed the residual paths for simplicity reasons, so I could control it. But if I had to reconsider, I probably should have kept. I should reintroduce the residual paths to get around overfitting. Then we have the output layer. It's actually quite an interesting problem with the output layer because I had to split up into the independent output layers. I couldn't just use one. I had to use one for the classification. And when I'm talking classification in this, I'm talking, is there a skin disorder or is there not a skin disorder? That's basically what we're interested in when classifying this. The second thing we're doing is actually a regression problem, where we're trying to do a region proposal based on the bounded boxes. And then we get these four values, the x, h, w, x, y, and you can see what the meaning of these parameters are on the picture. It's basically just parameters for the bounded box. And that's how we split, how I split the output. The model is basically 19 layers consisting of 2 different blocks. The first block that I used was 2 convolutional layers followed by a max pooling layer. And the second block I used was 3 convolutional layers with a max pooling layer afterwards. It's pretty common stuff, nothing fancy about that, about using max pooling layers or reducing dimensions in that fashion. I use Gloroid uniform initializer, and then I regularize with the L2 regularization. So I did do something to provide or prevent overfitting instead of using residual paths or vanishing and exploding gradients in this. When looking at the data and comparing it to the final usage of this, there's a potential problem. The potential problem is that the data used is of clinical settings and not of everyday settings of people having taken a picture of some mole they're having. Because when people do that with their smartphone, the skin disease might be off-centered, the lighting might be different, there might be hair, there might be all kinds of things that we haven't considered in clinical pictures. So that's a problem when we're looking into the usage of this kind of disease, or this kind of algorithm on this kind of disease. But otherwise, the data is pretty awesome. I mean, there's a bunch of doctors, a bunch of studies that worked. I can't imagine how many hours they're using this, but it's pretty awesome. And the doctors, it's all based on studies, so it's all validated by doctors or consensus of doctors. So we should think about the segmentation and the labels as pretty high quality when doing this. And yeah, I just use a simple 80-20 training test split. Nothing crazy about it. When I was doing development and testing, I was just using the batch instead of using the entire data set of those 20,000 pictures. So that's why I didn't use a development set. I just used the batches when developing. When looking at the model performance, I achieved an 89% accuracy, and that's for every parameter. Every parameter of the x, y, xx, xw, xh, I was 89% accurate in predicting those when using the model. And I'm actually pretty I mean, it's a huge problem, and there's a lot of things to do, but I think it's a good benchmark. In the beginning, I had something like, what was it, 60% accuracy, 50% accuracy before doing some changes that I wrote the ADD. So I'm pretty stoked about this. I don't have an intersection of a union metric, even though it could be applied in this particular instance. When we're talking about the model algorithm, it's basically we take the picture, resize it to the correct dimensions, then we normalize the pixel values by dividing the values by 255, and then we normalize it to a range of 0 to 1. Then we feed it to the model, and then we have the two different output layers that ends up in 99% or some percentage of how sure we are that there's this skin disorder in the picture, and it ends out in this proposed region. So we basically say, okay, we're not 99% sure that there's a skin disorder in this picture, and we're pretty sure that it's in this range right here. When rounding off, there's a lot of potential for the further use of this algorithm. I mean, as I said at the beginning, this is just the first step in a larger algorithm in tracking and diagnosing and all that kind of work with skin disorders. So a lot of potential in this kind of stuff. I should probably keep working on introducing the intersection of union as a metric, so that I can actually compare the bounded boxes, the ground truth bounded box, with the predicted box. So I have those two to consider with each other instead of just having a squared error, because that's what I'm using right now. Furthermore, I really need to consider the data distribution. Where's my training distribution coming from, and what am I actually going to use it on later on? So right now it's from clinical pictures, and I'm basically training the model to look at clinical pictures and diagnosing based on those. But in the end, it's going to be used by end users who's not getting right light, or they might have hair in their mole or something like that it hasn't seen before. It might be a weird angle. You might see, I don't know, a nibble if it's close to that, and that will definitely screw up the algorithm. So in order to improve it, there should be a data generation of handheld smartphone pictures to do this, to improve the algorithm. But that's basically all I've done. Basically all I've done. That's the presentation. I hope you enjoy it. I hope you learn something. I'm looking forward to keep working on deep learning projects and keep learning about this kind of stuff. So take care.